Well, I think it's trying to record, but okay, yeah. All right, so today's lecture is about one-loop renormalizability of gauge theories, that is Yang-Mills plus fermions. So first of all, we have to define the diagrams. And then, in principle, we should calculate their divergent parts in order to be able to renormalize. However, since actually there are 30 diagrams, this is too much for the QFT course. I mean, you can do yourself some of them. I think I leave some of them as exercises. But I will just present what the diagrams are and what the result of the calculation for the divergence is, and comment on it. All right, so there are five classes of divergent diagrams, Feynman diagrams, corresponding to the 5 1PI endpoint functions that are divergent. So the first one that is divergent is the gauge propagator. Of course, this, so that is to say, we calculate the contribution to the self-energy sigma mu nu. And well, as I've explained before, this reduces due to gauge invariance to so the Lorentz structure is encoded in this factor p squared delta mu nu minus p mu p nu, and also it's diagonal in Yang-Mills in gauge indices, so it's proportional to delta AB. Now the 3 divergent diagrams are written here. So you remember that we have 3 gluon vertices, but we also have 4 gluon vertices. And being that this theory is non-abelian, there was a determinant coming from the Fadeev-Popov procedure that was exponentiated into a ghost contribution in the action. So the ghost is a purely quantum object, but that means that it appears in loops. So in particular, we have a contribution with a ghost loop inside the gauge propagator. And there is such a loop because there is a vertex with 2 ghosts and 1 gluon. All right. So the divergent part of the example that we did last lecture was for the first diagram, the gluon contribution with 2, 3 gluon vertices, and also we had as an exercise the contribution with a ghost loop. And to remember that ghost loop comes with a minus because of its being an anti-commuting quantity in the path integral, the same way as the fermion is anti-commuting in the path integral. And well, we can calculate the contribution, the divergent parts of these diagrams, and we sum them up, and we find indeed that it's proportional to this structure that we said, the Lorentz structure, p squared w nu minus p mu p nu, and also the diagonal part in gauge indices, delta AB. It's also divergent, so there's a 1 over epsilon contribution. It's one loop, so it's proportional to g squared. That's important. Remember, I said actually one loop refers to the order in the coupling. So it could be that it's formally different number of loops, but if it's the same contribution in g squared, it's considered the same loop order. And also all of them are proportional to this C2G, which is the quadratic Casimir in the adjoint representation. In the adjoint representation, because the gluon themselves are in the adjoint representation. And yeah, so this contribution is because the quadratic gluon is the sum of TA squared. So each external gluon comes with a TA. There's also, I also wrote this. Observation is, as I said, usually one have this contribution of g squared over 16 pi squared. So when I said g squared, it's usually, the contribution is usually g squared over 16 pi squared times some small number, like in this case 5 over 3 in the Feynman gauge. But as you see, this is in a general gauge, it's alpha dependent, but in the Feynman gauge it will be 5 over 3. All right. The second contribution is for the Ghost propagator now. Now, of course, you cannot have an external ghost. As I said, the ghost is really a quantum object. It's something that appears because we exponentiate the determinant inside the path integral. So it cannot be external, but when we say propagator, we still mean that, so having exponentiated that determinant in the action, we still have an effective action that's path integrated over, including over B and C. So so I can write down a contribution that will renormalize the propagator in the in that effective action. So so in this very narrow sense, we can talk about 1pi contribution to the Ghost propagator. So I want to emphasize that that doesn't mean that the ghost is an external particle. There's no such thing. You cannot have external ghost. Okay. But then the contribution, the ghost couples only with the with one gluon. So there's a two ghost, one gluon vertex. So then the only possible Fermion diagram is the one that I've written here, with one gluon starting and ending on the propagator. So this I would call it self energy PAB, the same way as here I called it sigma mu for the gluon. And this divergent part is proportional to well, it's also divergent in gauge also diagonal in gauge indices, so it's proportional to delta AB. It's proportional to p squared because remember that the propagator is proportional to is actually the propagator itself is proportional to the Klein-Gordon propagator. And again, I've written this in a general alpha gauge, but in the final gauge, alpha equal to 1, this would be just one half here. And of course, it has to be proportional again with g squared over 16 pi squared and with the quadratic Casimir-Situde of g for the same reason. Okay. So these were the simple ones, but now comes a little bit more complicated ones. The contribution to the gluon 3-point vertex. Now there are 6 diagrams written here. So there's one diagram with 3 gluon vertices, right? So this one loop with 3 gluon vertices. Then there are 3 diagrams. It's actually just one diagram and 2 crossed ones for the case where I have 1 3 gluon vertex and 1 4 gluon vertex. So remember, the 3 gluon vertex is proportional to g, and the 4 gluon vertex is proportional to g squared. So this is g cubed. This is g times g squared, also g cubed. And then these 2 diagrams are the crossed ones to these ones. I mean, crossed is it's a definition. I can define, for instance, that these one are in and this is out. And then I can cross either this line or this line. And then I can also have a contribution with a ghost loop inside, because I also have a 3-point vertex, but with 2 ghosts and the 1 external gluon. So again, I have g, so g cubed. But now the ghost has a direction. On one side I have B, on the other side I have C, or eta and eta bar. So in any case, there's a direction associated with the ghost, in the same way as there's a direction associated with the fermion, the complex fermion. So I have 2 diagrams, one with direction like this and one with direction like this. And again, I can calculate the divergent part of all these diagrams and sum them over. And here, for simplicity's sake, I wrote that this is proportional to the classical, the 3-level vertex that I remember from last lecture I called V mu nu lambda ABC of KPQ, KPQ being the 3 external momenta, and mu nu lambda ABC, the corresponding indices of the external gluons. It's also divergent, proportional to 1 over, that is proportional to 1 over epsilon, also proportional to g squared over 16 pi squared, and with C2g. And again, in the Feynman gauge for alpha equal to 1, it's a simple number, 2 over 3. That will be always the case, that you have a classical vertex, the divergence part is 1 over epsilon, and then g squared over 16 pi squared. If there's a Yang-Mills, there's some structure here, some quadratic Casimir, and then some small number. All right, finally, not finally, but the fourth class is the 4 gluon vertex. Now there are actually 18 diagrams. So you see, when you go when you go up in the order of G, formally in loop order, but in the order in G, you get much more diagrams. So if I had the first order, sorry. Well, yeah, okay. So this one was I think I did something wrong here, because oh no, sorry. Yeah. So yeah, so you start off with this contribution. So the contribution to the gauge propagator is g squared over 16 pi squared, but then the propagator itself doesn't have any g. So this is actually ordered g squared. Now you go to the contribution to the 3-point vertex is this g squared over 16 pi squared, but then times the classical vertex, which is proportional to g. So this is g cubed. Then you go you go to the 4-point vertex. So it's again g squared over 16 pi squared times classical vertex, which is now proportional to g squared. So in all, this is g fourth. But you see, so the number of diagrams increases very fast. So here I had 3, here I had 6, and here I have 18, and then it goes the multiplicity goes up very fast. I'm not sure if it's exponential. I think it's factorial or something like this. But anyway, it goes up very fast. So Yang-Mills theory is at hard loop order. You have to do it with a computer, because otherwise it's really, really complicated. Well, I guess some people did classes of the diagrams, but I don't think. So I think the maximum Yang-Mills people have done is I think 4 loop, but with computers. Anyway, so the contribution to the 4-point vertex, as I said, there are 18 diagrams. And there's one which are just with pure glue everywhere in the loop. So there's this one loop with with 4 3-gluon vertices. So this is G4th. Then there's, I mean, the loop. It's kind of, I mean, this is sort of crossed diagrams, in the sense that I switch. If I switch, for instance, these two external lines, one with another, I get this diagram. Then if I switch this one, I get this diagram. But in reality, you really should think of this as sort of cross diagrams. And then you can think of basically contracting two 3-gluon vertices connected by a propagator. You contract the propagator such that you're left with just a 4-gluon vertex. So if you do that to this diagram, you can do it in 4 ways, right? You can contract these two, or these two, or these two, or these two. Correspondingly, you get these 4 diagrams. This 4 diagrams. 1, 2, 3, 4. And then you get 2 more by crossing, I guess. And then finally you can contract 2 opposing propagators, so that the 2 3-gluon vertices turn into 1 4-gluon vertex. So you can contract this and this and get this this diagram, or you can contract this and this and get this diagram. All right. So that's the way you should think about how to write down this set of diagrams for with just gluons, the one loop. And then the second contribution here are diagrams with a ghost loop inside. Remember, also for the gluon propagator, we had the same thing. We had the gluon loop or the ghost loop, for the same reason that I have both a 3-gluon vertex and a vertex with 1 gluon that I take to be external, and 2 ghosts that I take to be internal, or quantum. So so now I can think of this, but now I don't have 4 gluon vertices, so I don't have any contractions. I only have sort of crossings. But what I also have, if you remember, there's a direction. So I have this Feynman diagram with 4 sides, so with a square, but with direction, sort of clockwise direction or anti-clockwise direction. So these are 2 possible contributions. And then sort of crossing or switching of, so I can switch these two or these two, both for the first diagram and for the second diagram. In this way I get these 4 more diagrams. All right. So that's the contribution to of the divergent part to the 4-point gluon vertex at 1 loop. So it's proportional again with the classical one, classical vertex, written here as V mu nu rho sigma A B C D. As I said, this includes the G squared and also includes that complicated Lorentz structure with momenta and delta indices. On indices, it's divergent, so it's proportional to 1 over epsilon. And again, G squared over 16 pi squared and C2 of G. And again, in the Feynman gauge, so for alpha equal to 1, it's a simple ratio, 1 over 3. And finally, the last class of divergent diagrams are contributions to the ghost gluon vertex. So, the ghost gluon vertex is 2 ghosts, so the B and the C, and a gluon, A mu A. Now, what contribution can it be? Well, I can make a 1 loop here that either has 2 sides being ghost and 1 side being gluon, or has 2 sides being gluon and 1 side being ghost. So these are the 2 possibilities. But now the external ghosts have direction, well-defined direction, so there's no issue of switching the direction of the ghost. All right, so in this case, I have only two Feynman diagrams, and the sum of these 2 Feynman diagrams has the divergent part, again proportional to the classical vertex, defined here as V mu ABC, which also is, as I said, proportional to G. And then also G squared over 16 pi squared, C2G, and now a small contribution. So if alpha equal to 1 is 1/2. Well, times 2. Sorry, everywhere I wrote times 2 over epsilon instead of 1 over epsilon. Just because this comes usually from gamma of let's see, it's 2 minus d over 2. Yeah. All right, so these are all the possible divergent Feynman diagrams. Now we see that at 1 loop, we see that these correspond to the 5 3-level objects, propagators and vertices. So then are moreover are proportional to the classical parts, so the parts that come from the classical Lagrangian. Therefore, already we can you can decide that we have 1 loop renormalizability, because 1 loop renormalizability really means that the sum of the divergent parts corresponding to the classical object is proportional to the classical object. So so we can already decide, but let's think a little bit more generally and also more systematically. So in general, one would need gauge invariance to ensure renormalizability, because that would generate relations between Green's functions through the word identities. But in order to have a propagator, a well-defined propagator for the gauge field, we had to consider a gauge fixed formalism, because otherwise there would be a singularity. But we do know that when you fix a gauge, you have a residual gauge symmetry. We know that from QED, for instance, that fixing the Lorentz gauge allows still for a residual gauge symmetry, which what means residual gauge symmetry means there's a gauge symmetry whose dependence on space-time, so the parameter of the gauge transformation, let's call it alpha of x, or in the case of Yang-Mills, alpha A of x, a priori would be an arbitrary function of space-time. But that for the residual gauge symmetry, it's not an arbitrary function of space-time. It's something that depends on space-time in a constrained way. Right? There is some constraint on the way it depends on space-time. Now, in the case of Yang-Mills or general gauge theories, this residual gauge symmetry is called a BRST symmetry, and that will be studied in the next lecture. And we will see that just as we have relations between Green's functions similar to coming from the word identities, also we have from BRST symmetry relations among Green's functions similar to the ones coming from word identities. And that will allow us to prove renormalizability functionally before drawing down diagrams and computing them, before doing any computation. That will allow to define renormalizability in a general formalism. But okay, we've written down a bunch of diagrams, and I mean, not we, but someone computed them and saw that they're all actually divergent. So that's fine. But do we know that these are the only ones? So if I just have pure Yang-Mills, so just A mu A, this is the only field. Well, and B and C at the quantum level. Then the superficial degree of divergence is 4 minus the number of external gluons, EA, minus 3/2 times the number of external B's and C's, ghosts. Now, I've written for QED a similar formula, but with fermions. So minus 3/2 times of the number of fermions. And the reason was really that the propagator for the fermions is proportional to 1 over p. It's 1 over p slash ip slash plus m. But the same thing applies here as well. though the derivation is slightly different. So in the case of so the derivation of this formula is different, but the result is the same. So the Ghost propagator itself is proportional to 1 over, I mean, it's 1 over p squared. It's the Gluon propagator. So we had the first term between b and c was just del squared, right? But then the interacting part, which gives the vertex, was d mu ba gp fabc a mu b cc, which means there's this del mu, which gives a momentum. So the vertex with a b and a b line, a c line, and the gluon comes with a factor of momentum. But since each propagator ends in 2 vertices, so each Ghost propagator must end in 2 vertices. Effectively, we have an extra factor in the propagator. So so let's say I have one external B and one external C. It has to be this way because, remember, there's an arrow. It's the same as for the fermions, so they come, external number comes in pairs. But then in here, there's always a vertex, and here there's always a vertex. And inside, we always have, effectively, we have a line that ends in a vertex here and a vertex here. So so because of this, effectively, so think of this as being this as being half a vertex, half a vertex. So together they make a vertex, which is proportional to p, and then the propagator is 1 over p squared. So effectively, the propagator is 1 over p. So effectively, it acts like for the fermions, which means I get this 3/2 times the number of external B's and C's. All right, so now that I have this formula, let's check that the 5 1pi endpoint functions that we found to be divergent are actually the divergent ones. So if I have 2 external gluons, so the Gluon propagator, then I have 4 minus 2 is 2. Then if I have 2 external gluons, so 2 external ghosts, so the Ghost propagator, then I have 4 minus 3/2 times 2, so 4 minus 3 is 1. They have, then if I have 3 external gluons, so correction to the 3 gluon vertex, it's 4 minus 3 is 1. I have correction to the 4 gluon vertex, so 4 external gluons. It's 4 minus 4 is 0, which is still divergent. And finally, the Ghost Gluon vertex, in which I have 1 external gluon and 2 external ghosts. So 4 minus 1 is 3, minus 3 halves times 2. So 3 minus 3 is 0. That's also divergent. So these are all the divergent ones. You can check yourself that there's nothing else that can be divergent. Well, okay. And if you don't believe this, we will see more formally how this happens using BRST symmetry in the next lecture. All right, so now let's consider the counter terms in the minimal subtraction scheme. So minimal subtraction scheme means that we just subtract the divergent part, the ones that we've written really above. So so the divergent. So we write a contribution then to the gluon propagator as Z3 minus 1, as usual, times this part that gives the gluon propagator. And then Z3 has the 0 order, which is 1, plus the 1 loop order, which is, well, minus what we've calculated here. So what we calculated here was minus this thing, g squared over 16 pi squared, and blah, blah, blah. So, so minus the divergence is added to the action. Now, from the Ghost Propagator, also the same thing. We write Z3 tilde minus 1 times this Ghost Propagator contribution. And then this has the 0th order is 1, and then the 1 loop contribution is minus the divergence. So we add minus the divergence to the Lagrangian. All right. So indeed, we've seen that, well, let's go back to the Ghost Propagator. And so this was minus g squared times p squared delta AB. So now it's plus g squared, and then times p squared. And p squared comes from minus del squared from the propagator. So indeed, we've added minus the divergence to the classical Lagrangian. Now, from the 3 gluon vertex divergence, again, we've defined this to be Z1 minus 1 times the 3 gluon term in the action. And then, again, this is times minus g squared over minus the divergent. So, well, again, minus g squared times the classical vertex. So this is correct. Same thing from the 4 gluon vertex. again, Z4 minus 1 times this 4 gluon contribution to the Lagrangian, and then Z4 at 0 order is 0, and at 1 loop order is plus G squared times blah, blah, blah. And this is, again, minus G squared plus times the classical 4 vertex. And finally, the ghost gluon vertex, again, Z1 tilde minus 1 times this ghost gluon interaction. And then Z1 tilde is the, at 0 order it's 1, at 1 loop order is minus G squared. And in here, we had plus G squared times the classical contribution. So again, we add minus the divergent part. So the Lagrangian plus the counter term Lagrangian, which is minus the divergence, depending on so the things to be renormalized are the fields A, the quantum fields B and C, the ghosts, the coupling G, and the parameter alpha, which is a parameter in the effective action for the gauge fixing term. And then that is equal to the renormalized. Well, so that's the renormalized one, and as I said, numerically it's equal to the bare Lagrangian, depending on the same things with 0, the bare quantities. Right. Okay, so how do we renormalize? Well, we see, so we'll look at this renormalization. We see that we have 5 quantities, A, B, C, G, and alpha, that needs to be renormalized. But 2 of them must be renormalized in the same way, B and C. B and C are, well, ghost and anti-ghost. As I said, one way of thinking of them is eta and eta bar, which, as usual, must renormalize in the same way. So really, there are 4 things. But on the other hand, there are 6 coefficients. We've written here L plus delta L as being, well, there's this gauge field propagator term. There's this gauge fixing term. There's this 3-point vertex term. There's this 4-point vertex term. There's this ghost propagator term, and two ghosts, one gluon vertex, right? So another way of saying it, there are the 5 contributions to the things that to the 1pi objects, plus this 6th term that comes from the gauge fixing term. So 4 objects to be renormalized, but 6 coefficients for 6 terms. That means that we should also obtain 2 consistency conditions. So we renormalize 4 things, and then the remaining 2 should be automatically renormalized. So let's check that. So we renormalize the gluon with Z3. That was, Z3 was defined to be the coefficient for the gluon propagator, the one loop gluon propagator. So from the renormalization condition, we see that we have the bare quantity A0 is square root Z3 times renormalized A. And the same thing for the Ghost Propagator. We have Z3 tilde, the renormalized term. And then this is sorry, the one loop contribution. And so the renormalization of B0 C0 is the these bare terms is square root Z3 tilde BC. Now, in principle, we should also write so we should also renormalize in principle the gauge fixing term, but we already written that A0 is square root Z3A. So substituting this in here, you see that we get a Z3 over alpha 0, and then this d mu a mu squared term cancel. So alpha 0 must be equal to Z3 alpha. All right. So this seems to be automatic renormalization. And then for the 3 vertex term, 3 gluon term, through Gluon Vertex, we have Z1 and 3 A's, and the coupling G. So substituting the renormalization of A, that written in here, that A0 is square root Z3A. So we get, on this side, we get Z to the 3 halves, G0. And on this side, we had Z1. So G0 is GZ1 over Z3 to the 3 half. All right. So we've taken care of, so we've renormalized 4 terms. And now it remains to check that that the remaining 2 terms are also renormalized correctly. Well, I also have a 4 gluon term, which is proportional to G squared A to the 4th. And the renormalization is with a new kind of parameter, Z4. So I have G that is renormalized with Z1 over Z3 to the 3 half. So G squared will be renormalized with Z1 squared over Z3 cubed. And then A4 is renormalized with Z3, square root Z3. So A4 will be renormalized with Z squared, Z3 squared. And correspondingly, substituting this in here, okay, it's a little bit difficult for me to write with this one, but you can check yourself that the relation, basically there's a relation between Z4, Z1, which came in the normalization of G, and Z3 that came in the normalization of A. And the corresponding relation is this one. Z4 over Z1 is equal to Z1 over Z3. And finally, the last term that needs to be checked is for the Ghost Gluon Vertex. So for the Ghost Gluon Vertex, we have found that I have to put, the Ghost Gluon Vertex is normalized with a factor Z1 tilde, but then G, B, C, and A, they're all renormalized already. So I will get a relation between Z1 tilde, G is normalized with Z1, A with Z3, and B and C with Z3 tilde, right? So B and C with Z3 tilde, A with Z3, G with Z1, and when you substitute everything, you get another relation that it's useful to also write as a equality of two ratios, Z1 over Z, and also moreover the ratio is the same as the right hand side. Here is Z1 over Z3 is equal to Z1 tilde over Z3 tilde, which was really why we call these things with tilde. Together, these two relations are called the Slavnov-Taylor identities. And at this point, it's not clear why they should be correct. As I said, really what happens is that such kind of relation normally appear from gauge invariant, but from gauge invariance to the word identities that relates various 1pi endpoint functions, and so their corresponding Z coefficients. But since we work in a gauge fixed formalism, we don't have gauge invariance. What we do have is this residual BRST invariance. And so next lecture we'll derive the Slavnov-Taylor identities from BRST symmetry. But the only thing that we can do right now is to check explicitly at one loop that these two equations are satisfied. And now we have to remember that Z's, all the Z's are written as 1, which is 0th order in loop, plus Z at one loop. And here we must do that funny thing that we talked about. Even though the Z1 loop is divergent, is proportional to 1 over epsilon, it's also proportional to G squared, and G squared is supposed to be small. So we expand in G squared, therefore we expand in this Z1 loop. So substituting in here 1 plus Z1 loop, which is supposed to be small, what we get at one loop, so here this is 1 plus Z1 loop, Z4 one loop, here this is 1 plus Z1 one loop, here is Z1 plus 1 loop, Z3 one loop. So correspondingly, what I get is I get Z4 one loop, so expanding. So 1 over 1 Z1 one loop is also 1 minus Z1 one loop. Then multiplying with this, I get 1 plus Z4 one loop minus Z1 one loop. Right? And here I get 1 plus Z1 one loop minus Z3 one loop. Or in other words, Z4 one loop is this combination 2Z1 one loop minus Z3 one loop. And similarly from this one, I get that Z1 one loop is Z1 one loop plus Z3 tilde one loop minus Z3 one loop. And we can verify this. We've written the corresponding divergences. We can just substitute these formulas. So this Z4 one loop is this thing, this Z1 one loop is this thing, and this Z3 one loop is this thing. And correspondingly, you substitute into this equation, you see that is satisfied. And here as well, Z1 tilde one loop is this thing, Z1 one loop is this thing, Z3 tilde one loop is this one, and Z3 one loop is this one. And again, you check that this equation is satisfied. And now, next, we consider what's really more important, to have a gauge theory with fermions. The reason why we think about this is because the application we have in mind is the standard model, in which case we have fermions coupled to gauge fields. So we have QCD with quarks coupled to SU3 gluons, and electroweak with SO2 cross U1 coupled to doublets of fermions, left-handed fermions. So because of that, let's consider gauge theory with fermions. So the Euclidean action for the fermions is written here, and the covariant derivative that appears, so d mu, we think this is ij for the fermions being in the corresponding representation. So this is psi I, is psi bar j, let's say, is the diagonal part, the unperturbed part, d mu delta ij, plus this contribution with a gluon, a mu a, that is proportional to g, and also with the generator TA in the representation f within cis ij. And now the superficial degree of divergence in the presence of fermions is the same thing. I mean, already calculated what it was for fermions. We just added this thing for ghosts. So we know it is 4 minus E gluons minus 3/2 E fermions minus 3/2 BC. So that means that besides the 5 one-point functions that were divergent that we calculated before without EF, now I have also and also you see EF corresponds to EBC. So I have 2 more, since I had 2 with external ghosts. Now I have also 2 more 1 pi functions with external fermions. So that's the fermion propagator, sigma, with 2 external fermions. So it's 4 minus 3/2 times 2, or 1. And the 2 fermion, 1 gluon, 2 fermion, 1 gluon vertex, gamma A mu alpha beta, which is 4 minus 1 gluon minus 3/2 times 2 gluons. That's 0. However, so these are 2 more things that are divergent and renormalized. But before analyzing that, let's consider the case of let's consider the contributions to the 1 pi endpoint functions already considered in the pure gauge case, coming from fermion loops, right? So it's really, wherever we had the ghost, we can also substitute with the fermion, because the same thing happens. There's it's fermionic, and there's a vertex with 2 of these, either 2 ghosts or 2 fermions, and 1 gluon. So so like we said for the, like we said here, so we said we had this contribution to the gluon propagator. So there was the pure gluon contribution, but there was also this ghost loop propagator. And now we have the corresponding fermion loop propagator. Okay. And we can calculate the divergent part of this. It's again proportional to g²/16 pi squared, and divergent proportional to 2/epsilon. The only new thing is that instead of C2G, which was coming from 2, external TAs, 2 external generators, so giving the Casimir C2G. Now I have this TF, which is TR, that is to say the trace of 2 TAs in the corresponding representation. In this case, the representation is for a fermions. It's so instead of TR, I have TF. And so so what I had was trace TATB in the representation R is equal to TR in the which is this T in the representation R, times delta AB. And now TR is TF. So this was a contribution to the gluon propagator, that is to Z3. And then I have also a contribution to the 3 gluon vertex. Again, the same thing. If we look at 3 gluon vertex. Yeah, look at the 3 gluon vertex. You see that there's a contribution due to a gluon, a ghost propagator, one going anti-clockwise, one going clockwise. And correspondingly, now there will be also a contribution with a fermion loop going anti-clockwise or clockwise. So these are these two contributions. And you calculate also the contribution of these two diagrams, and you see that the sum of these two diagrams is equal to the sum to the one diagram above. And that's good, because remember that we had, at one loop, we had these Slavnov-Taylor identities. So by adding contributions to the extra contributions to them, so they were satisfied with the previous calculation. So now by varying them, I should also get contributions. I should also get equality. So now if I vary Z1 and Z3, but Z1 tilde and Z3 tilde are not modified by adding the fermions. So I get that this Slavnov-Taylor identity is not modified. And yeah, there's a problem that here Z4 is modified. Oh yeah, sorry, yeah. So there's also corresponding. Sorry, yeah. So there's also Z4 is also modified. Again, the same thing. So the 4-gluon vertex was modified by adding these ghost loops, which I can now replace with fermion loops. So one can calculate also this variation to delta Z4 and see that delta Z4 is equal to, at one loop, with delta Z1. So delta Z4 would be equal to delta Z1, and then delta Z1 with delta Z3. So the contribution to these, to the left-hand side, to the right-hand side, cancel independently. And here we already shown that this is satisfied. All right, so so let's consider the new terms in the new 1pi endpoint functions. That means the new terms in the Lagrangian. So we have the fermion propagator, which divides into the part proportional to del mu, that is proportional to p mu, and the part in the mass term. And there's the vertex 2 fermions with a gluon. Correspondingly, I have Z functions, ZF2, ZF1, Zm. And the counter term is Z minus 1, right? Then Z is equal to 1 at 0th order, and at 1 loop order is equal to minus the divergent part. So yeah, so well, we can calculate, and you get this result. So now these Zs are proportional to CF. So C2G, so the corresponding terms in the Lagrangian without fermions were proportional to C2G, which means the quadratic C2G is the quadratic Casimir in the joint representation. But now with external fermions, we have something that's proportional to CF, that is the quadratic Casimir in the fermion representation. It's also proportional to g squared over 16 pi squared, and with the divergent 2 over epsilon. All right. So the corrections to the fermion propagator and to the 2 fermion and one gluon vertex are exactly like, well, I didn't write them here for some reason, but they're exactly like the ones for ghosts. I mean, it's really the same thing. So to be more precise, so this is the diagram for the correction to the ghost propagator. So if you replace this ghost line with a fermion line, that's the correction to the fermion propagator. So it's just a fermion line with a gluon line making a loop on it. And then the correction to the vertex, the correction to the 2 fermion, 1 gluon line is the same as this correction to the 2 ghost, 1 gluon line. It's this diagram plus this diagram. All right. Yeah, here I define what CF and TF were. And just to check, so this was for a general gauge theory, but of course we can specialize to the case of QED, which we already calculated. So, and we can check consistency, that we obtain the same result that we obtain in QED. So in the QED case, so for an abelian group, CF is 1. So this is the quadratic Casimir, which means the sum of TA squared. But of course, TA is trace TATB. So of course, this is just 1, but trace TA, but the quadratic Casimir TA sum over TA squared is actually 0 in this case. Let's see so the one way to think about this is that really TA with indices ij is equal to 0. That's one way of thinking about it. Whereas in the adjoint representation, sorry, that TA in the adjoint representation for QED is equal to 0, but in the fermion representation is equal to 1. So that's one way of thinking about it. So you just substitute these formulas. So C2G equal to 0. That means, well, almost all the calculations before were equal to 0. So the only non-zero things were the ones with fermions. So renormalization of the new terms come as usual. So we add these 3 terms, and then this should be equal to the numerically equal to the bare part in the Lagrangian. So by renormalizing, let's say, first psi, we would say that psi and psi bar is equal to square root of ZF2 times psi and psi bar. Now, once we do this, I have, once we do this, well, we see that also ZF2 times psi bar psi is also equal to psi bar 0 psi 0. So this term is taken care of. So we're left with just normalization of M with Z M. Oh, right. So yeah. So that means that I have to, yeah, I have to put ZF2 in here as well. So since ZF2 psi bar psi equal to psi bar 0 psi 0, then I have that MZM is equal to M0 ZF2. So these two renormalizations are extra renormalizations. I renormalized psi and M, which are the 2 extra things that I added to my Lagrangian. But then I also added one more term. So this vertex now gives a constraint. So there's this new renormalization object ZF1, but everything else is renormalized. G, psi, A, they're all renormalized. So by writing this, I get, so A is renormalized by Z3, G is renormalized by Z1, and psi is renormalized by ZF2. And this term itself is has an ZF1 in it. So that means I have to have a relation between ZF1, ZF2, Z1, Z3. And the relation, you can check this out easily. That is the one that I wrote in here. ZF1 divided by ZF1, ZF2 is equal to Z1 over Z3. And again, we can check explicitly that this is satisfied at one loop, the same as in the pure gauge case, meaning I have, so on the left-hand side, I have approximately 1 minus ZF1, 1 plus ZF1 one loop minus ZF2 one loop equal to 1 plus Z1 one loop minus Z3 one loop. And then we can you can check this at one loop. But now this is an extra Slavnov-Taylor identity, and moreover, also like in the two previous ones, I have the right-hand side is Z1 over Z3. So all in all, the Slavnov-Taylor identities can be written as ZF2 over ZF1 equal to Z1 over Z3, and is also equal to the previous two things, namely Z1 tilde over Z3 tilde and Z4 over Z1. All right, so so that's it. Then by adding fermions, we have seen that we find also that we have three identities between the renormalization factor Z. All right, and the next lecture, as I said, we'll talk about, well, BRST symmetry, and but before that we'll talk about asymptotic freedom, which is the whole point of the whole reason why people introduced Young-Mills theory. I mean, Young and Mills just wrote an action, but then asymptotic freedom was the reason why this was taken to be a good theory for QCD. All right, so this is everything that I wanted to tell you today. Do you have any questions? All right. Can somebody check that they can still hear me?
Yes.
All right, good. So that means that you really don't have any more questions. So so that's it then. I will we'll start next lecture on Thursday at 9, as we've decided. So Thursday at 9, I'll see you again. Bye.